an announcement in the Slack, and then
Yeah.
we give it,
and we can wait a few minutes.
a few minutes so people can transfer over.
Well, you weren't kidding when you said they had backgrounds from hell.
Oh, well, electron recoil, you can't separate stuff, right? You just have to
Yeah.
make everything super clean. You have no, normally you use the electron recoil as the tag of background to then, veto all your background, right?
Yeah.
This is the same thing with super CDMS, right? That when they do the electron recoil and the Luke effect, I think it's called.
Yes. Yes, that's right.
The reason they were able to say something interesting is just because no one had looked in that area before, and then pretty quickly you get to the backgrounds, and then you stop being able to say more until you go deeper underground or something.
And this is where for an electron recoil search, this is where a big detector like Xenon 1 ton is helpful, because you don't have to worry about the gamma rays at all. You just have to worry about your internal contaminants.
Because of self-shielding.
Yeah.
Yeah.
And then if you're just looking at low energies, you can figure out what the beta spectrum is at high energies and build a model that's pretty good, except for tritium. And also except for argon-37, which they didn't talk about at all. that's what most of the chatter on LZ is about, is why don't they have argon-37 in their background model?
So why except for tritium and argon-37? Well, argon-37 I can kind of guess, because argon and xenon are both noble gases and they mix together happily.
That's part of it, yeah. But really it's because there's no high energy indicator for this. So you can't do... You can't base your background model off of what's going on at high energies.
No sideband to normalize off of.
Yeah,
essentially.
Exactly.
Okay.
Yeah.
No way to calibrate your background.
Yeah.
Is argon-37 also like a really low energy beta or something?
Argon-37.
Is it just it doesn't have a gamma with it? I remember you said something about this yesterday.
Yeah. So argon-37 is kind of neat. It's an electron capture decay, so you don't get anything except a neutrino and an excited...
And the nuclear... I guess not a recoil. Do you get a recoil?
You don't get the recoil, you get the relaxation of the... Let's see, which way does it go? The relaxation of the chlorine nucleus.
I see. So you get a gamma ray.
No, sorry, the chlorine atom. It's a decay to the chlorine ground state, but you've got, since it just ate a K-shell electron,
you get an X-ray from
coming out.
Characteristic X-ray. Okay.
Yes, but the characteristic X-ray is right at threshold.
We have a question from a student. Take a look at the chat.
Oh, sweet.
Is that the argon you mentioned at the start? Yes. So we use argon-37 as a nice calibration because it gives you a monoenergetic line. Presumably they put that in after the WIMP search, but it can be there before you inject it also. And so if you imagine putting in a low energy peak, it shows up about where, it's just barely above threshold. So it's, let's see, what is its energy? It's at like 2.7 keV or something, and their threshold's at 1 keV. So if you have any softness of your threshold at all, or any loss of energy resolution, it'll just look like it's a rising or a falling spectrum instead of a peak.
But that's good, right? Because that lets you measure your threshold turn on.
It lets you measure your threshold turn on, yeah. It's just surprising that they didn't include it in their background modle, because I mean, it would end up having a similar-ish effect to tritium, I think, where it could just, I think it'd be even more actually. It would, I think if they floated the amount of argon-37 in the detector, my guess is that it would, that would kill the significance of the ABC effect. it's showing kind of those energies. But okay, maybe we should share screen.
Okay.
We're up to 50. We're up to 50 people, 42 attendees.
Okay. Great. So that was fun. I hope everybody was able to tune in earlier to the Xenon 110.
I had technical I had, you know, clueless technology user technical difficulties. And then I somehow like hit an arrow key and jumped back 5 minutes in the talk or something like that. So that was, at that point I decided I'm just gonna like read the paper later.
Let's see. So, oh, this is looking different than it did the other day for some reason for me. Oh, it's okay. I can see the chat. Okay. So let's see, should we go ahead and get started then? Do you want
do you want me to say who you are? At this point?
Sure.
Okay. All right. Okay. So people know at this point who Eric is, but Eric Dahl from Northwestern is going to give his third and final lecture on dark matter experiments, direct detection.
Yeah, and what I think we're going to do, I do want to start out a bit talking about detecting wave dark matter, which includes detecting axions, completely different method than the Xenon 110 result we just heard, which is also detecting axions, maybe the same axions. And so, yeah, so we'll have a bit of a lecture and then we'll throw it open to just discussion about what hopefully you were able to just hear from Xenon 110. I think when we get to that, I'll give, you know, a 5-minute overview of what Xenon 110 saw, and then we'll just start a discussion that I'm sure will continue in the discussion session. Okay, so yeah, no, all the links there as usual. So let's share. Yep, that's shared, and I need to get back to the beginning here. Okay, so yeah, you know, for this sorry, I need to gather my thoughts because it's been an exciting last hour. So for these 3 lectures, you know, the charge was to talk about all of direct detection, and that means not just direct detection of particle dark matter, but also direct detection of wave dark matter. And it's, you know, I want to spend some time paying attention to at least, you know, one of the big wave dark matter experiments, because one, it's relevant to what we just heard from Xenon 110, although not directly relevant, but there are ties there. And also there's just some really cool things you can do if dark matter happens to be, say, the QCD axion, and are able to figure out what the axion mass is. Then it opens up huge avenues for, well, for basically dark matter astrophysics, which is neat. So okay, quick reminder: what do we mean when we talk about wave dark matter? So we're talking about ultra low mass dark matter, so stuff below an EV. And you heard last week, I know, that if dark matter's this light, it's got to be bosonic because you can't fit that many fermions in one galaxy, thanks to the Fermi exclusion principle. And kind of going along with this is the idea that it's going to be bosonic dark matter with multiple particles in any given mode. So we're really talking about now something that looks more like a classical field than individual particles. And the way you detect it is by looking at the oscillation of that field rather than the interaction of individual, you know, quanta of that field. Here, I'm waiting for my touch screen to start working here. Maybe I have to click a couple times first. So this is I hope people read XKCD. This is a really old XKCD, but this is basically the idea of how detecting wave dark matter works. So somebody's jiggling their leg up and down and the whole desk starts to resonate, right? And what we're doing is we're saying the dark matter, this oscillating field, is the leg jiggling up and down, and our detector is the desk that's resonating. Of course, that will only happen if we can get a good resonant coupling between this oscillating field and the dark matter. So, sorry, my There we go. My stylus finally turned on. Okay, so first thing we need to ask then is, how narrow is this dark matter frequency? Because we've got this oscillating field. It's got some frequency that's fixed by the mass of this boson, whatever it is, but also, it's got some kinetic energy as well. And having a velocity distribution means we've got some frequency distribution just for the bosons that are flying through through our detector in the lab, right? So if we want to say, how do we turn this line width and velocity into a line width in frequency space? Well, okay, we can say d omega times d beta is, and beta here. So if the velocity changes, the frequency changes. And so if we want to say the width in frequency space is going to be m times beta times the width in velocity space, or if you like, the relative width of this thing is going to look like beta delta beta. If we divide by to zeroth order, the frequency of this oscillation is just the mass. And so this relative width of this line, which you can think of as, if this were an oscillator, 1 over the Q value is, okay, beta is about 10 to the minus 3. The width is also about 10 to the minus 3. This is about 10 to the minus 6. This means that if we're watching this oscillator, it looks coherent for about 1 million oscillations. And that's what we want to take advantage of. That's what, we want to be able to see 1 million oscillations of this field piling on top of each other. And that's what's going to make it possible to detect this. Okay, so we'll call this Q. This basic statement about the Q value, this isn't specific to any particular wave dark matter. But from here on, we're going to talk about axion dark matter. So we're going to call this the Q value for the axion field is about 10 to the 6. Okay, so how do we detect this? This is, the leg bouncing up and down, but now we want to have this coupled to a desk that's rattling. And you want the desk also to be a high Q resonator so that it can, so it itself is also coherent at this kind of 10 to the 6-ish level. So let's sketch what kind of the idea of the ADMX experiment is. So we've got this oscillating dark matter field. And now we're going to go ahead and say, let's suppose this is a QCD axion. I don't know if people have talked about QCD axion yet. I haven't looked through enough of the lectures. But this is
Eric?
Yes?
Your audio is starting to break up a bit. Could you maybe try turning your video off?
Yes.
And there's also a question in the chat.
Yes. What is Q again? So you can think of Q as in 2 different ways. If you've got anything oscillating, Q is the 1 over the relative line, width in frequency space. So you have a very narrow resonator that's high Q. Q is also, if you've got, say, just an oscillator with some stored energy on it, it is, let's say, it's the energy stored in the oscillator over the energy lost per period. So if you've got an oscillator and it's being damped, that's what gives you some line width, right? And so if it's damped, you're losing some energy. You lose some fraction of your energy each oscillation. 1 over that fraction is your Q value for the resonator. So there are a few ways to think about this. You can say the line width is narrow enough that if I look at this oscillating field now and I look at it 1 million oscillations later, it will still look coherent. It will still have the same phase. Or you can think of it as if I've got a cavity and I've pumped it up to some amount of energy, then the time scale for that energy to drain away is something like the period times the Q value. So things fall out after an average 10 million, 1 million oscillations for a Q of 10 to the 6. Okay, so we've got our oscillating axion field here. And it's coherent if you're talking about QCD axions, you're talking, and you want them to be dark matter, you end up with axions that are oscillating at about a gigahertz, which means with this Q value of 10 to the 6, your coherence time is about a millisecond. And with these things traveling at 10 to the minus 3, your coherence distance is about 100 meters. So you can really think of this field as being coherent across something the size of a football field and coherently oscillating up and down for, macroscopic time scales. In particle physics, a millisecond is a really long time, right? So we can just think of this field as being completely coherent. And now we're going to drop a resonator in here. And our resonator here is just going to be an RF cavity. So if you think back to electricity and magnetism, this is just a waveguide with the ends capped. And what we're going to do is we're going to look for something called the Prima effect, which was one of the effects we just heard about in the Xenon 1 ton presentation, if you tuned into that, where we're going to get an axion converting into, in this case, an RF photon. And that happens if you have the axion field in an externally applied magnetic field. So we're taking this RF cavity, we're putting it in some external magnetic field, and we're going to look for photons to appear in this cavity. So what does a photon in a cavity look like? It's just a standing wave, a standing electromagnetic wave, right? So the standing waves in this category that we're going to look for, it turns out you need to look for the modes where you're creating an electric field that's parallel to the magnetic field that's causing your Prima conversion to happen. So we're going to get electric fields oscillating up and down in the cavity like this. So this is our electric field for our RF photon that's gotten trapped in the cavity. And if you're interested, we call this the transverse magnetic 010 mode in here. And you've got magnetic fields going around in the phi-ish direction. And we're just going to look for a photon to appear in this cavity, or maybe multiple photons. And the thing that always takes me a while to remember here is that, you don't want to think of this as, one axion going to one photon. That's, we're used to thinking about, with the last two lectures, one dark matter particle comes in and it creates one event. Here, it's really, you're having, you're reducing the occupation number in the axion field by 1, and you're increasing the occupation number in your cavity by 1. And it's the coherent contribution of this entire field that makes this a measurable process. Otherwise, the coupling would be far too small. Okay, so what are your considerations in trying to make this happen? Okay, we need to design a cavity. The big question here is, what resonant frequency do you want to make your cavity at? And the problem is, we don't know. So figuring out what frequency this needs to be is, I don't know, it's the billion-dollar question. Because if we knew what frequency the axion was, we could just build a cavity there and we could find dark matter tomorrow. But we don't know, and so we have to make a cavity that's tunable. Because, there isn't anything in the QCD axion theory that tells us what the mass of the axion particle should be. That's just a free parameter. It's kind of the one free parameter in the theory. So we have to build a cavity that looks something like this, where we've, instead of just having a cavity, we have a cavity with like a dielectric rod going down the middle, and we can move that dielectric rod back and forth in the cavity. And when we do that, what that's going to do is scan up and down in frequency space in the resonant frequency of the cavity so that we can look for axions of different masses. And this is what ADMX does. If we look at the actual Admx detector, so they have things exactly like this. They actually have two tuning rods. They swing these things back and forth. And as they do that, the resonant frequency of the cavity changes, and they can look for axions of different masses. Now, any one of these cavities, they can tune to kind of a factor of 2. We'll talk more about the y-axis in this plot in a moment, but if we just look at the x-axis, this ADMX experiment has been running for years, and they've scanned, kind of this much, not quite a factor of 2 in frequency space. The challenge here is that, we really don't know what the mass of the axion is. If axions are dark matter and they're the QCD axions, then we can put maybe a lower limit on the mass. But there's at least an order of magnitude that for dark matter is interesting to look at. So really, if you say what we've scanned so far is kind of this much, so that's done after a couple years of searching, and this is the goal. So there's a lot of work to be done just slowly scanning through this space. But if you happen to hit the right frequency, and we'll talk about what that would look like in a moment, if you happen to hit the right frequency, you know it instantly. So it's one of the really exciting things about an axion search is you could find dark matter tomorrow, and you don't have to wait for stats to build. You just suddenly tune into the right frequency, and your detector comes alive with a dark matter signal. So any day, ADMX could come and tell us, hey guys, we found dark matter, it's axions, we're done. So that's what makes this kind of an interesting game. What else can we say about this? Well, okay, so we're going to design a cavity. What Q value should we have for this? This is worth pointing out because certainly if we have a big Q value for our cavity, that basically means you can pick up more cycles of the oscillating field before the energy starts to bleed out of your cavity. So a high quality cavity leads to more signal. Up to having a cavity that has a similar quality value to the axion field itself. So if your cavity has a Q value of 1 million, that's kind of as good as you can do. There's no point having the line width of your cavity be narrower than the line width of the axion mass. But there's a downside to, there's a question. So can they do that tomorrow? Yeah, ADMX is running right now. Would they tell us the next day if they thought they had a signal? No, but you'd hear about it within a month. They would do their checks and they would, make the biggest splash they could about it. We'll talk about the smoking guns. Oh, does the Xenon 110 result give them an immediate hint on where to search? That's a great question, and unfortunately the answer is no. Even if Xenon 110 is seeing axions, what Xenon 110 sees doesn't give you any information about what the mass of the axion is, which is what ADMX would need in order to find it. We'll come back to that when we talk about what Xenon 110 is looking for and how it's a little bit different from this. So, okay, so big Q cavity gives us more signal. The problem is that if you have a really high Q cavity, that also means narrower window for resonance, which means you have to scan more slowly. You have to scan more different frequency windows. I can spell resonance. You can't read it with that handwriting, but the upshot here is that means it slows down the scan if your Q is too big. So what Q value should you actually use? And it depends if you know what you're looking for or not. You know, if you don't know what you're looking for, probably you just go for a cavity with a 10 to the 6 Q value. But for the QCD axion, you can actually say how strong you think the axion coupling to the E&M field is. So this is, you know, this is our coupling between the axion field and the cavity. And this is, you know, a specific QCD axion model. I guess they have two different models there, but this kind of gut sort of axion models really set what this coupling should be, and figuring out then what that signal would come into here. There's an assumption that this is 100% of the dark matter, right? Because it's going to matter how, you know, how many axions are going through the detector. But if you say it's a QCD axion and you say it's 100% of the dark matter, and we say we know the velocity distribution, then you can just stop when you get there. This dark green versus light green here, these are actually, you know, two different velocity distributions. One's a little bit narrower than the other, and if it's narrow velocity distribution, you're more sensitive to it. I forget, one of these is the Maxwell-Boltzmann distribution. The other one is something from, you know, a little bit more in touch with the astrophysics. But it doesn't make a huge difference. And so their goal is they want to be able to see a signal that can rule out this basic QCD axion if it's 100% of the dark matter. And they can do this based on the quality of how well they can measure the cavity and other things like the magnetic field in the cavity. They can do this with a Q value of about 10 to the 5, which means if they can do that, they can scan 10 times faster than if they had a Q value of 10 to the 6, because they've got a broader resonance to look at. Okay, so they've chosen their cavity, they've chosen a resonant frequency, but they're going to try to tune it. They've got a Q value. How big should the cavity be? So we didn't talk about...
There's a couple of questions, actually. Yeah.
When will the frequency of ADMX be extended to much larger range? Great question. So we'll talk about why that's hard on this slide in a moment. What are the timescales over which they need to check the resonance? Is it like a sweep and imagine it'd be really quick and then we can span over large frequencies? So I don't know the exact answer to this. I think they spend something like, you know, order 10 minutes, half an hour on each frequency window, and then they'll move to a new position. So, you know, they'll have, you know, each of these lines that you can see, kind of the 1 pixel thick lines, that, you know, that would be one scan. And so you can kind of look at how many of these have they done, and that's how many they did in 1 year. And, you know, they do many scans a day. It's not like a 1 minute scan, but it's not like an hour scan either, is my impression. But it's just, you know, they're carving out very narrow slices with each scan. It's really what sets how long they have to sit at each frequency is the noise floor of their amplifier. So they are trying to dig into the noise, and it's, you know, they're kind of doing a background subtraction of the noise, if you will. So if they sit there and they look at signal for a bit longer, they can dig into that noise. And I'm really going beyond my expertise. So apologies to any ADMX people if I'm getting this wrong. Okay, but when will the frequency range of Admx be extended to much larger range? Okay, so that's tied to this question of how big do you want your detector to be? So, the rate at which, axions convert to RF photons, that's proportional to, it's proportional to how strong a magnetic field you put on. It's proportional to the Q value of the cavity, and it's proportional to the volume of the cavity. So you want a big volume. So a big volume goes to more signal. But you've got a problem, because if you just do a basic cylindrical cavity, volume, goes like some linear dimension cubed. The resonant frequency goes like 1 over that dimension. And so your volume goes like 1 over your resonant frequency cubed. Now, you can make weird shaped cavities to try to get a big volume, but also have a high resonant frequency. But when you do this, you start running into things like mode crossings in the cavities, which make it so that having too many different resonant frequencies close to each other ruins your Q value. It's, I think, one way of looking at it. Again, apologies to RF cavity experts. But this is why they haven't gone to a much larger range yet. Where they really want to go is to higher mass axions, which means higher frequencies. But if they do that with this style of cavity, the cavity gets too small for them to be sensitive to the dark matter. So what they need to do is they need some way to coherently add multiple cavities. So they're going to have multiple small cavities, coherently combine their RF signals, and then search that way. But that means, of course, to coherently add multiple cavities, those cavities have to be at exactly the same resonant frequency. And so they have to have a method to actually lock multiple cavities at the same frequency. So there's, a lot of RF cavity design and some kind of neat, how do you tell when you're on resonance with regard to some baseline clock that you're looking at in order to achieve this. But that's why it's hard. And they're doing R&D to figure out how to get the next factor of 2 in frequency space. And then maybe to go to higher or lower ranges, you do something completely different. Instead of having an RF cavity, you can actually do it with just an LC circuit. Anything with that oscillates like this kind of has a different mass range that it's sensitive to. But okay, so this is, just to take one big cavity and divide it up into many small cavities. What makes this too naive? So I'm kind of naive about these cavities myself, so I'm not certain of the answer. If you had one cavity and divided it up into small cavities. So if we come back here, it has a little bit to do with what modes we're looking for. So we need modes where you've got your electric field parallel to the B field, because that's how the Prima conversion works. So breaking this up into cavities stacked on top of each other actually would not help, because in this mode, the frequency is goes like 1 over the radius of this thing. So you couldn't stack things on top of each other and help. You could talk about dividing it into a bunch of lobes, either azimuthally or, kind of have pockets at different radii. But it gets into a problem that, it's still, is it one cavity or is it multiple cavities? If it's one cavity, you're going to get more degrees of freedom, and you're really going to end up with, instead of having one mode in all these different cavities adding coherently, you'll get a lot of different modes close to each other, and you'll get energy sloshing back and forth between the cavities, and something about that makes it so that you lose energy from the system. And that's as much as I can remotely intelligently say about that. So instead, what you really need are completely separate cavities where you read the signal from each cavity, but you add that signal coherently. You can think of it as, you're measuring the E field in this cavity, and then you add those measurements together. And you can do that as long as, but then you have the problem that you've got these different cavities that need to be tuned so that they're at just the right, so that they're at the same frequency, so that when you add the E fields that you measure in each of them, things are still coherent. Okay, so let's talk about what an axion discovery would look like, because that's what makes this really neat. So the neat thing about axions is that you have a lot of smoking guns if you see a dark matter signal. So say ADMX sees an increase in power at a given frequency. The first thing they check is, does the signal disappear off resonance? Because they're relying on the, they can measure the frequency of the signal directly with their amplifier, and they can check. So I guess what I'm trying to write and talk at the same time. So they can independently look at the power coming into their cavity and the frequency of what's coming into their cavity. Okay, so it's not just we tune the cavity to this frequency, we see power, so the power must be at that frequency. No, they can also say what's the frequency of what's actually happening in the cavity. And if they get a signal, so for instance, they hear an actual terrestrial radio wave signal, and that happens, if that signal is there, whether or not the cavity is at that resonant frequency, then it's not dark matter. Then they can say, does the signal go away? Or does the signal depend on the B field that they apply? And if it's an axion, it's better. And they can check the line width. So remember, there's a natural line width to the axion signal that's, okay, if this is a gigahertz axion, the line width of this is about 1 kilohertz. And it's easy to get frequency resolution at the kilohertz level, so they can actually map this velocity distribution and see if the velocity distribution matches the astrophysics. And then, once they've done that, they can look for modulations, just like in dark matter, just like in particle dark matter, that velocity distribution changes with the seasons, and they can look for that. Now, you'd have to wait for a year to see, or at least half a year to see this modulation. That modulation is kind of at the hertz level. And you might think it's tricky if you've got a gigahertz frequency that you're measuring. Can you measure this kind of line shape at the hertz level? It turns out, yeah, you can. Frequency is one of the easiest things for experimentalists to make precision measurements of. So a part to 10 to the 9, part to 10 to the 10 measurement in frequency is actually very doable. In fact, they can not only look for the modulation in the annual modulation, just you think of it as the Doppler shift from the rotation of the Earth. They can look for a daily modulation, not in the direction of the signal, like in directional detection, but they can just in the velocity distribution. You get kind of millihertz shifts in this velocity distribution daily, and they could even look for that. And the coolest thing that they can do is they can actually start doing Axion Astronomy. So what do I mean by this? Suppose we're in some infalling halo, some infalling stream of dark matter. So suppose there's some dark matter stream. And what I mean by a stream, that means there's some flow of dark matter at a well-defined velocity. And it might be a small fraction of the total dark matter we see, but it's going to give you a peak in this velocity distribution. And that will show up as a peak in the frequency distribution seen in the Axion detector. And they can look at that and they can say, they can watch this thing move back and forth with the seasons. They can watch it move back and forth with the day. They can actually reconstruct the direction that that's coming from by comparing the modulations with season versus modulations with the day, and just looking at how does the Doppler shift of this peak in the velocity spectrum move around. So, if axions are dark matter and we're in a dark matter stream, we can actually point to the direction that that stream is coming from by looking at how its frequency moves around during the day and during the year. And that's just remarkable to me that you could do this. There's no way that you could do something like that with particle dark matter, where we've got such a small signal to work with even once we find it, and you'd be looking at a dark matter stream of a small fraction of the dark matter in the lab. But for axions, or wave dark matter in general, once we know what the mass is, then it's easy to detect. You can detect loads of it, and you can do all of these cool things. So even though I don't look for axions, I almost wish that this turns out to be what the dark matter is, because there's so much that you can do with it. So okay, that's kind of my spiel on wave dark matter. And then we can flip to xenon 1 ton. Okay, I don't see questions popping up. So let's flip to what xenon 1 ton was just talking about. So I was copying and screen capturing and pasting slides on here as the talk was going on. Evan gave a great talk on this. Impressive that they gave a grad student this talk to give. So in 5 minutes, what did we just hear from xenon 1 ton? So this was an electron recoil search. So, their normal WIMP search, they're looking for nuclear recoils. That analysis came out a while ago. They have an electron recoil background because they've got beta decays in the detector. This is why all of the particle discrimination we talked about yesterday is so important. But they have, let me back up, go forward. They have models for what this background is, and it's mostly one beta decay or another, but there could be interesting electron recoil signals on top of this, including signals from solar axions. So these are still potentially QCD axions, and it's okay, and this ties in really well with the question that just showed up. Question, I thought the axion was a particle. Why is it treated as wave dark matter? Well, here we're going to treat it as a particle. So it's really a question of, are you looking at the coherent effect of a lot of axion bosons all in the same mode? In which case you're thinking of it, we're in ADMX, they're not detecting single axions. They're detecting the collective, an excitation resulting from the collective effect of millions of axions. And that's really kind of why we call it wave dark matter instead of particle dark matter. It's kind of has to do with how it appears in the dark matter halo. You've got occupancy numbers of your modes that are large, and so we think of it as a field instead of individual particles flying around. But here, we're not talking about detecting axions as a wave anymore. We're talking about detecting axions that aren't part of the dark matter halo, rather axions that are made in the sun, and due to the process that they're made in the sun, are coming out with high energy, keVs of energy coming out from the sun. And in that case, we detect them as a particle. it's analogous to saying, it's like, if you turn on the radio, we're detecting electromagnetic fields. We don't talk about that as detecting individual RF photons when you're tuning your radio. But if we're talking about gamma rays or X-rays, we do talk about them as individual particles. It's really analogous to that. So Xenon 1 ton was doing a search for axions produced in the sun. Could be the same axion field. But in looking for it this way, these would be relativistic axions. So Xenon 1 ton isn't sensitive to what the mass of the axion is, because they're just seeing, highly relativistic particle coming in. And they can't say whether the axion is the dark matter or not. So you could have an axion field that's not the dark matter, but is still being produced in the sun. And Xenon 1 ton would see that. Why do we say Xenon 1 ton can't determine the mass range when the talk showed that the axion is between a micro and milli eV? So that is the range where the axion is if it's the QCD axion and it's 100% of the dark matter. So that's, but Xenon 1 ton can't add any information to that. And in fact, if the QCD axion isn't the dark matter, then, well, okay. I guess the QCD axion, assuming it's going to be produced in the early universe, and if it's less than a micro EV, then you have too much dark matter. So that's a lower bound. And yes, that is a model dependent claim. But within the QCD axion paradigm, I think you can say it's a pretty good lower bound. Well, it depends on the production methods in the early universe too, but you usually don't talk about QCD axions being less than a micro EV because you get too many of them and you'd have too much dark matter. If the QCD axion is higher mass, then you have less of it for dark matter. And so if you say all of it's dark matter, then you're looking in kind of maybe an order of magnitude range of masses. If you don't require it to be all of the dark matter, then you can get to higher masses. I think you get up to a milli EV when you're, and above that, then you have other astrophysical bounds coming in from, I don't know, things like magnetars maybe, or something like that. This is really beyond my expertise. But that micro EV to milli EV range, that's basically coming from bounds of what we can say about QCD axions. So Xenon has no sensitivity to the mass of the axion. Then it could be that Xenon is maybe detecting an axion which is not dark matter. Yes, that could be. It could be that the QCD axion exists, but that it's not the dark matter. And that, but it could still be produced in the sun, and Xenon 1 ton could still see it. Can it become even higher like GeV? So I know as you go higher in axion mass, you run into astrophysical bounds from looking at big magnetized objects out in space like neutron stars and white dwarfs. And I don't know the details of that. I've never heard anybody talk about axions up, above the EV range. But okay, so Xenon 1 ton was looking for axions. They could be the same axions that Admx might see, but instead of being produced cosmically, they're produced in the sun, and they're being produced relativistically, giving you enough energy to give you a signal in the Xenon 1 ton detector. So it's basically one of these axions comes in and bounces off an electron in your detector, and that's your signal. But the problem is that you've got all of these other electron recoil backgrounds in your detector. So if you see something like this, where, okay, you've got a signal that's climbing at low energy, then how are you going to distinguish that from a beta decay with an endpoint around 10 keV? Or how are you going to distinguish it from anything else going on in your detector? So let's look briefly at their background model. I'm not gonna, they talked a little bit also about, about neutrino magnetic moment, but maybe we won't talk about that right now. So this is their basic background model, and you can see the sorts of things that go into this. These are all different electron recoils. Materials means it's gamma rays. Everything else here is basically a beta decay. Actually, xenon-133 is also gamma rays coming out. They've got solar neutrinos in the mix. The big one is lead-214. Just, any of these experiments that's at low energy, that's the main background. They talk a little bit about, now, let's see, where did I know I saved this slide. They talked a little bit about the sort of pathological backgrounds that we were looking at yesterday. For instance, they mentioned accidental coincidences, and they basically said, oh, apparently I didn't have that slide, or I overwrote it. So the idea is that if you're trying to understand your signal for low energy electron recoils, you're depending entirely on sidebands, right? Most of your backgrounds do have a high energy piece associated with them. So when they build these background models, these are all anchored off of what's going on at higher energy. This lead-214 beta, for example, that goes up to hundreds of keV. And so they can look at the shape of their background model, and they can determine based on what's going on at high energy, how much of each of these components exists. Same thing for probably most of the pathological backgrounds here, because their pathological backgrounds would have shown up in their WIMP search. Because remember, in the WIMP search, they're already looking for, 1, 2, 3 events. And here they're looking for, many dozens of events over background. So kind of, you could say that their pathological backgrounds, they've probably already addressed those in the WIMP search. And they did mention something about accidental coincidences. And basically the answer was, yes, these would have shown up in the WIMP window, and they didn't. And so we don't have to worry about them in this window either. So if you look at their background model, so there's the actual backgrounds that they measure. And yeah, at high energies, their background model works well. And then this is what they see at the lowest energies. So this is their background model based on what they see at high energies, and they start seeing this excess below about 7, 8. Well, really, I mean, maybe they start seeing an excess here, but they definitely see an excess in their lowest energy bins. And then at this point, it falls off because that's the threshold of their detector. So that's what's falling off here. And so the question is, what did they see? And it's really hard to say. This is an effect at threshold. And understanding effects at threshold, they're always the hardest things to do. The background that they talked about most in the talk was tritium. Tritium, if you throw tritium onto this background, it looks like this red curve. So the addition, so the tritium spectrum looks like the orange dotted line down here. And if you add some amount of that orange dotted line onto their normal background model, then they can certainly become consistent with what they observed. There's another background that they didn't talk about, which is argon-37. They calibrate with argon-37, and argon-37 gives you a peak that would look basically like that. This would be, so since I've switched to my mouse, I can't write anymore, but this is, where argon-37 would be. And they may have reasons why they don't consider argon-37 as a background. They inject it into their detector on purpose to calibrate. One reason you wouldn't think it'd be argon-37 is because it shows up as a peak, and this runs up all the way to their threshold. But if their threshold moves around a little bit, or if their energy calibration moves around a little bit, you could easily have the argon-37 peak showing up looking kind of like this. And so that's I'm sure something that was brought up in the Q&A there. It's certainly something that my LZ colleagues are asking. But yeah, so for these reasons, because there are backgrounds, both this argon-37 background and this tritium background, the reason they can't exclude them is because there are no sidebands. They're entirely within the signal region. They're just normal electron recoils in the signal region, and so they really can't distinguish these from the Axion signal, which is why they can't claim a discovery. They can argue why they think these backgrounds are low, and that gives you, some hope that this is a real signal. But these are extremely difficult backgrounds to rule out, because it's this catch-22 that the only tool you have to look for these backgrounds is your dark matter detector itself. And if you can't tell these from the signal, then you can't claim a discovery. So that's kind of the bind that they're in. It's a bind that LZ is going to be in too, if LZ sees the same thing. So okay, let's take questions in the chat. What do we think is going on with Xenon 1 ton?
Actually, maybe can I ask a question? Oh no, there's one here. What are the sidebands? I think I missed that definition this morning.
Okay, so I mentioned sidebands yesterday. So when we're trying to build these background models, sidebands means looking at some place where you're not looking for signal. It's in order to validate your background model. So sometimes sidebands could mean, oh, I did have this slide in here. So for instance, looking for accidental coincidences, which was one of the pathological backgrounds we talked about yesterday. Yes, you could have accidental coincidences showing up in your signal region, but we know what the distribution of accidental coincidences should look like. And so you can look outside your signal region and see if that background shows up there. And in this case, it didn't. So that's what we mean when we say a sideband analysis. For electron recoils, the only sidebands you can look at are things outside your energy region of interest. So you look at higher energies than where you would where you would have signal, and you build your background model based on that. The problem with both tritium and argon-37 is that they don't do anything outside your signal region. So there is no rate in a sideband for you to anchor these off of. Okay. Based on the last lecture, it's not uncommon for new pathological backgrounds to come up. What does it take to be convinced it's not some weird pathology we haven't come up with yet? It takes a lot, especially for something that's happening very close to your detector threshold, because that's where we understand these detectors the least. So it basically takes looking at many different analyses of this. One thing that they mentioned that I think is in the paper, which has just been posted, hadn't had a chance to read it yet, is looking at what does this signal look like in the S2 only analysis. So they can go to lower threshold by looking at events where they don't get an S1 and an S2, but only an S2. When they do that, their backgrounds go up because they don't have position reconstruction anymore. But there may be something interesting to see there. But yeah, it's basically, you just have to look at this in as many different ways as you can, or have it confirmed by another experiment. Now, LZ is going to turn on in less than a year, and it's going to see this if it's real. But it's the same style of detectors. You'd have to worry about the same pathological backgrounds. Yeah, what's the plan for the future? The tritium background will always sit on top of the signal. So there are things you can think about. So sometimes we inject tritium in order to calibrate the detector. And we can inject tritium and watch it come back out. One of their arguments about tritium was, well, if it was in there, we would purify it out. Now they haven't done that in their detector. Some of these xenon TPCs do inject tritium and then watch it come back out, because it's a really useful calibration source, precisely because it's in this energy region of interest. So if you did that and it all came back out, that would be one argument that, well, tritium can't just hang out in this detector unless you have some continuous source resupplying your tritium. And you could say, based on how well we can pull tritium back out, how big would that source have to be? Is that reasonable? And you might come out and say, yes, it is reasonable, or you might say, no, it's not. And I think it's, I think the argon-37 is the harder one, but I didn't hear their answers to those questions. Is xenon the only experiment looking at this energy range? No, many experiments look at this energy range, but xenon is the biggest. So the other experiments looking here are either small things looking at much lower, going down even lower in energy, but because they're smaller, they wouldn't be sensitive to a rate this low. Or you have things like large liquid argon detectors, but liquid argon is really not great for looking for electron recoils because argon is radioactive. Liquid argon works great for looking for nuclear recoils because you get enormous discrimination there. We didn't talk about this yesterday, but there are ways to get great discrimination in argon. But for electron recoil searches, it's weaker. So there really isn't anything that can match xenon here. Xenon 1 ton has got the lowest electron recoil backgrounds in the world. That means they're the most sensitive to this, at least until LZ or xenon N ton turn on. Neutrinoless double beta decays don't look this low in energy, the experiments, so they wouldn't be sensitive to this either. So tritium included, it's one high bin, the second one. What about statistics? Well, you know, if they include tritium, they said it dropped down to like a 1 or 2 sigma effect. It was certainly no longer a 3 sigma effect when they included tritium. They had that number. I don't know if I wrote that one down. Yeah, I don't think I did. So we'd have to go back and look at the paper. We can come back to that this afternoon. Isn't near threshold anomalies always tricky? Yes. What do I personally think of the results? I think this is going to get me in trouble. No. What do I personally think of the results? I mean, this is hard, right? This is looking at something, you know, in terms of energy. This is, well, it's the same energy window where DAMA sees its modulation actually, although this is, you know, this is a much lower rate than what DAMA sees. But it's just showing you that when you get down to these energies, things get really hard. So to me, this looks like, you know, at the higher energies, these are statistical fluctuations, and those 2 bins that are high are, you know, the most likely explanation to me is tritium or argon-37. But it's tantalizing, right? And, you know, it shows that we have to work harder in those backgrounds and then see if this goes away. Okay, since the Axion and neutrino models which fit the excess are ruled out by astrophysics, which is more probable, astrophysics being wrong or the flux at the Earth, assuming the excess is because of Axion or neutrinos? So this is a question to me of how model dependent are the comparisons between astrophysics and this. I tend to believe the astrophysics bounds because I know how hard it is to really understand your backgrounds at the low energies. I need to look again at those specific astrophysics bounds though. What do I think of the large fluctuation? Oh, the one that my mouse is over here. I think that if you look for a large fluctuation in a lot of data, you're going to find a large fluctuation somewhere. You know, picking picking this out is, you've got to take into a big look elsewhere effect to say that this is significant. The bump around 15. Okay, so here where they're floating all three different axion couplings, I mean, that's 3 free parameters on something that's pretty flat. It's not surprising that they can fit all of this. This bump is not significant. This bump is really not significant. The only thing that's significant, in my opinion, is really the ABC axion coupling hitting these low spins. But that's where you worry the most about threshold. What is the look elsewhere effect? That's a great question. So the look elsewhere effect it's basically calling out the problem that if I ask you the question, is there anything weird in this data? You have to be really careful about how you answer, right? So if I said, look at this point looks like it's, I don't know, 4 sigma below the background model. Is there something wrong with the detector that it's suppressing events at that energy? And there might be, but I only asked that question after I looked at the data. I'd have to instead ask a question, saying, that one point by itself, okay, maybe it looks like it's 4 sigma down, but I have to include the fact that I chose to look there in the first place. So the look elsewhere effect is kind of saying, the statistical question I should be asking is, what's the probability that if I had 40 of these data points, that one of them at least would fluctuate down this far? And then it becomes a much less significant effect. That's, in a very small nutshell, what the look elsewhere effect is. Low stats experiments always have to worry about this, because when you've got low stats, there's going to be something that catches your eye. It's the reason why we do blind analyses. My favorite example of this is the Auger experiment was trying to, looking at ultra high cosmic rays, and you get, one of these a month or something like this. And they wanted to do their analysis in real time, but they had to have a probability budget for what sort of things were they going to look for in where these ultra high energy cosmic rays came from. And they were only allowed to publish their internal rules, or they're only allowed to claim correlations that they had claimed they were going to look for beforehand, and that they were only going to look for things so that the probability that they'd see anything accidentally was less than some value. I don't know, 1% or something. And as a demonstration of this, I saw a seminar where somebody said, here's real old Auger data, and we're going to look for Elvis. So you just turned the raw data dump into an ASCII stream and said, let's see how often the word Elvis shows up in the raw data. And is there a statistically significant excess or not? And it turned out there was a statistically significant deficit in the word Elvis in their data. And so we concluded that Elvis had been kidnapped by the aliens. Just a cute example where if you're saying, I'm going to look for something weird, you'll find it. Sorry, I spent too long on that, but the look elsewhere effect is really important in those stats experiments. About astrophysics, my impression is that stellar cooling constraints and supernova constraints are best understood for axions specifically versus generic new light species. Okay, so that's saying it does have model dependence in it. A lot of calculations have been done in detail for the axion case and got repurposed for the other approximate applications. So while constraints like this are sometimes regarded as imprecise for your favorite dark matter model, they are relatively robust for axions. Would anyone with more experience like to comment? I don't have more experience, so I'm not going to comment. But yeah, that's, yeah, I think that's driving home something about, when you're talking QCD axions, you don't have that many parameters to play with. And so you can make more robust ties between completely different types of experiments than you can for a lot of other types of dark matter. Okay, were there any questions in the chat that we missed? I don't have a lot of Axion experience, but I had the impression that their Axion results are not in tension with other constraints. They do disagree with a different anomaly. Yeah, so unfortunately, I was distracted at this point in the Xenon 1 ton talk by chatter on the Lux Zeppelin Slack page. So I'm an LZ, which is the chief competitor to Xenon 1 ton, Xenon N ton, and so we obviously had a lot to say about this. So I missed what they said about the astrophysical constraints actually.
I got the impression from, I flipped through their paper and looked at the plots, and it looked like for the for the neutrino magnetic moment, their best fit, if it were solar neutrinos with an anomalously large neutrino magnetic moment, that best fit value from them was in, it's the slide 20 of the ones you've got there, was in significant conflict, or I mean, some amount of conflict with the astrophysical bounds. Yeah, because like the blue bar is their fit, but then the astrophysical constraints are different. And I don't know where these come from. Well, Boraxina, I know what it is, but but I don't know where the other ones come from. But for the axions, I think it's like there's part of their parameter space that's excluded by other stuff, but part of their parameter space which is totally still allowed. But in agreement with Ethan, it doesn't agree with this stellar cooling anomaly. I mean, I guess one of the nice things about axions is it's a well-defined particle physics model. It has some couplings, it has a mass, and then you can just like do particle physics with it. And the axions that they would like, if they're seeing axions, these axions are axions just like radiated out of the sun. These aren't the coherent dark matter axions.
Right.
I mean, if it might be the same axion, but it's like saying, it's different individual axions.
So in other words, if ADMX does come out with a signal, that will add a lot more credence to the axion interpretation of what Xenon 1 ton just saw. I think is a fair statement.
Yeah, I think so. Actually, if Admx detected an axion, they would know its mass, and then wouldn't they also then know at least one of the couplings?
So,
but that's model dependent, of course. Oh no, but they have the signal strength.
They're assuming some value for the Prima coupling.
Right.
So I don't know enough axion physics to know. So for this GA gamma, ADMX assumes a value for that. That's what these two, well, I guess they assume two different values for that. That's where these two lines come from. So those are specific models, and I don't know how, many different, I guess I don't know how well constrained, just from a theory standpoint, that coupling constant is. Xenon 1 ton kind of treated it as completely open. ADMX doesn't.
Honestly, I kind of have no idea.
There are a lot of things called axions. The QCD axion, axion-like particles. I agree.
There is a nice discussion of the vocabulary in Anson Hook's TASI lectures from 2 years ago. mean, there are the QCD axion is something very, very definite. You know, you solve the strong CP problem. There are all these relations. There are moduli and string theories. There are all kinds of stuff out there. But there's two parts to the discussion here, and one of them is there a signal in the detector, which is a question which is independent of the preprints which will appear on HEP-PH tomorrow saying that these guys have discovered some particular kind of axion.
Yeah, for sure.
Maybe a naive question. Oh, let's see. Okay, I'm going to punt on the heavy axion question because I can't speak intelligently to that. But the next question: how are bins chosen in general? Since there is just the second bin higher in the background when tritium is included, increasing the first bin by rebinning the data may decrease it. Is it something reasonable? So they said they did an unbinned likelihood analysis. So the bins here are actually just for plotting purposes. And if you only pay attention to the statistical significance, then the binning won't matter. So how are the bins chosen here? They probably chose 1 keV bins. And you know, or they chose the bins that made it look like the best fit to the eye. They probably didn't do that. They probably just chose 1 keV bins, but the statistical analysis itself didn't rely on the bins. Okay.
Okay. Any other questions? Maybe I can say something about the super heavy axion question. So I think there it depends on what you mean by axion. I think if an axion when you get down to it is a pseudoscalar particle, so a spin zero parity CP odd particle. The QCD axion has some special couplings. Like, I mean, it's introduced to solve a particular problem, so it has some like special things about it. I think people have talked about just generic pseudoscalar particles in certainly the heavier mass range. But I don't know actually if you can call them axions. I mean, the thing I don't know about axions is if there's some particular like rule attached to an axion, like only derivative couplings or something like that, which is true for pions. I don't know if there's something special for axions that is like a precondition for calling it an axion, because heavier particles, people just usually call them pseudoscalars. An axion-like particle is sort of any pseudoscalar that's light, I think. So this could just be fuzziness in language, but it could be that there's some critical physics property of axions that I'm not aware of that determines whether you can call it an ALP or not. So like if you have a 2 Higgs doublet model, the pseudoscalar Higgs, the capital A is a spin zero CP odd particle, but we don't call it an axion.
I'm learning things. Okay.
Okay.
I should attend these.
Yeah, Julie's comment, I thought the axion has to solve the strong CP problem. I think usually people refer to that specifically as the QCD axion to distinguish it from other things that people have subsequently named axions. But I think originally the axion, like that name was coined for the particle that solves the strong CP problem. And then the QCD was added later after people started generalizing it. But maybe I'm not sure if I'm right about that history, but that's my impression.
So these days, do people use ALP to mean an axion that's not the QCD axion?
Axion-like particle.
Yeah.
I think I think people use it to mean any sort of like lighter than, 100 MeV pseudoscalar particle that kind of shows up in the kind of searches you'd use for, I don't know, those kinds of things.
So
it's a very generic term.
Is there a particle that you would call an axion that you would not call a QCD axion or an AOP? Or is axion just the catch-all term that includes kind of those two?
Axion is a catch-all term. Axion-like particle, if you want to be slightly cautious, but many people are not slightly cautious. The interesting thing for what you are talking about is that the axion couples to FF dual. That gives you all of the wave stuff you were talking about there, the E.B interaction. So any particle with a coupling to gauge fields, which is of the FF, the phi FF dual form, will be the thing that an axion detector could detect.
Where F is the photon field strength.
Yeah. And of course, for the QCD axion, the axion couples to the gluon field strength times its dual. But
in addition? Like in addition to the photon field strength?
Yes, yeah. I mean, it has to, right?
Oh, to do the strong CP thing.
Yes, to do the strong CP. But you detect these things. You have axion-like particles which can couple to FF dual. FF dual is E.B. That's the origin of Eric's comments about the particular modes in the cavity which you want to excite, right? And the Primakov effect. It's actually a very nice, almost a Jackson problem to work out the electrodynamics for an axion-like particle. And the Primakov effect is you are using the static magnetic field as one of the parts of the F nu, and the other one is a is a dynamical field.
Yeah.
But I think I said this once, but I'll say it again. There are two issues here. Do they see something in the lowest part of their spectrum, and then I think it's premature to go off and and write papers about the discovery of some of my the particular version of the axion that I happened to write down back in 1995.
Sure. Yeah. Oh, Lauren has a comment, and I think this is why this product of the mass and the F, which is the scale, the new physics scale, essentially the
Yes. She is completely correct.
Yeah. But this is why it's a straight line in the models, right? The prediction of the QCD axion is why it's a straight line on those plots, because 1/F controls the coupling strength, and then the mass is on the x-axis. So if you fix the product and you plot it on a log scale, you get a straight line.
All right.
Yeah. All right.
So,
we should probably wrap up, but yeah.
Yeah. So I'm going to propose that we continue this in the discussion session this afternoon, where between now and then, I'm going to dig into the experimental side, see what my colleagues have learned about the argon-37 background and threshold effects and all that, and we can talk about what do we think of this excess from a detector point of view.
Awesome. Yeah. So discussion session, just to remind people, is at 3:45 this afternoon, TASI time. And there will be 2 rooms. And basically the lecturers will start out one in each room and then swap halfway through. So whichever room you're assigned to, just be patient and you'll get Eric either first or second. And then Lisa Everett will be the other person in the discussion this afternoon. All right. So I think we're good. And see you back again at 10:45.